Hello, my name is Konstantinos Bousmalis. I'm a research scientist at DeepMind, and today I will talk to you about our recent work on cross-embodiment visual imitation, which we have worked on together with Yuxian Zhu, who was the lead on this project and also the creator of most of the content that you will see on these slides, and also Yusuf Aitar. Let me start with some motivation first. Why are we interested in third-person imitation at all? And I'll start by saying that this is a natural skill for humans. Humans learn new skills by imitation in third person all the time, and we do so from a very early stage, as demonstrated also with this cute video of this aspiring Rocky on the right here. And we as humans are able to observe behavior by others, process that visual information, and map it to our own embodiment in order to perform similar actions that arrive at the same results with what we are observing. Instead, in robotics, imitating just by perception other robots or humans performing complex tasks is still a very hard problem. It would be nice to have, though, and robotic learning usually requires carefully designed rewards, and we know that this kind of reward shaping and engineering does not scale to the kind of real world complexity that we're interested in. So we do want to crack the problem of third person imitation in robotics, as this could enable learning more complex tasks and learning them at a significantly decreased cost. It could make robots more useful by utilizing the abundance of visual data that exists out there. Let's make this more concrete. What we want to do is equip our robots with the ability of third-person imitation, specifically cross-embodiment third-person imitation. As an example, what I'm showing here is somebody in the lab using their hand to stack a red object on top of a blue object. And what we want our robot to be able to do is to understand what's going on in this video and replicate SAT's trajectories as precisely as possible using only vision. And I should mention that in this work, we are always imitating trajectories using this environment on the right in simulation. And our embodiment is a parallel gripper. It's a robotic gripper attached to a Sawyer arm. In order to be able to do that, there are a few challenges that we need to address. First, the challenges that have to do with imitating from pixels. We don't have access to action. It's almost impossible, for example, to define, let alone obtain actions for human demonstrators. There is no task reward, as in this scenario, we don't have a particular downstream task in mind. And finally, we either don't have proprioceptive information, or the proprioceptive information that we do have is different to the embodiment of our imitating agent. There's also more challenges that come from working with different embodiments, and on top of the human hand that I have already showed, which is one of the environments that we are experimenting with in this work. We also have a human operating a pickup stick and manipulating objects that way. We have a three-finger Jaco arm, and we have a real-world equivalent of our simulation environment. So it's a robotic gripper attached to a Sawyer robot in the real world. What we want is our agents to be able to imitate demonstrations collected with any of these embodiments and actually be agnostic to what embodiment was used, and where these demonstrations are coming from. There are some related work in this space, and works that have to do with imitation learning that handles gaps between demonstrations and the environment the imitator is acting on is done primarily on hand-engineered feature spaces. And when we talk about imitation from pixels, there's usually no domain gap, or the domain gap is particularly limited. For the few approaches that do manage to do imitation learning in pixel space from a larger domain gap, as you can see, for example, here, what happens is that these are model-based approaches. So there's a vision model that extracts, let's say here, a human pose, or here a body pose, and then they imitate these trajectories in simulation. But this turns the problem from pixel space imitation to feature space imitation. And our project tried to do specific imitation from both pixel space and also with very large domain gaps, uh, both in terms of embodiment, but also the reality gap as well. So our problem is imitation of third-person demonstration with different embodiments that are unseen during training, and demonstrations that are unseen during training, solely from pixel observations and with large visual domain gaps potentially. We start from a demonstrator providing a sequence behavior, and from that behavior, we slowly track frames that are embedded in a manipulator independent representation space. And the way this happens is the next goal observation is sampled from the demonstration, and an imitating agent is trying to reach that goal. So essentially, this is a tracking problem, is tracking the trajectory from a different embodiment and potentially from a different domain. Our solution to this problem is doing imitation via reinforcement learning. So we learn to follow a given trajectory in our simulated environment. And we do that with an off-policy reinforcement learning algorithm. In our work, we used maximum a posteriori policy optimization, or MPO, where our MPO agent was conditioned on the current observation of the imitating agent and the next goal that is sampled from the demonstration. And what our agent would then output would be the action to take that would get the agent closer to that goal. And in order to train this agent, we use the tracking reward, which is defined as the negative exponential distance between the observations and the goals in a learned embedding space. And this means that the current observation and the goal should be close enough in this embedding space to give a reward of 1. Otherwise, a reward of 0 is given for that frame. So we call this embedding space the manipulator independent representation space, or MIR for short. And the most important part of visual imitation by trajectory tracking is to have a high level feature space that can match demonstrator and agent observations. For this, we reckon there are 3 desired characteristics for such an observation space. First, it's cross-domain alignment. Observations that are semantically similar in two domains should map to the same representation. Temporal smoothness, temporally neighboring frames, regardless of their domain, should map to the same representation. And finally, being actionable, which means that the representations that we learn need to be suitable for reinforcement learning. And I will now go through how we dealt with each of these characteristics, or desired characteristics, in a bit more detail. For cross-domain alignment, what we did is we leveraged simulation and domain randomization, by augmenting simulation in 3 different ways and providing aligned trajectories that way. So we start from our domain randomized environments, which are obtained by starting from a canonical environment and randomly changing object textures and colors, light intensity, ambient colors, and camera poses, which were also slightly perturbed. And then we are also able to get a variation of our environment by not rendering our manipulator effectively. So we have this effect of objects kind of moving by themselves. So we see the effect of the arm, but not the arm. We have a version. We also have a version of the environment where we are also doing domain randomization, but only for the manipulator. And we obtained paired trajectories, aligned trajectories, by combining domain randomized with arm invisible trajectories, and domain randomized with arm randomized trajectories, and that creates a data set of trajectories that we then use for our representation learning. And I should note that this data set was collected in simulation with stacking agents that were pre-trained to stack one object on top of the other using the feature space that is available in simulation. So with this collected data, we are now able to learn the manipulator independent representation space that can align these paired domains. And one key property of this representation space that we want to have, as I mentioned earlier, is temporal smoothness. And in order to do that, we build upon time contrastive networks known as TCN, which is usually applied under kind of like a multi-view scenario. What TCN does is that it enforces higher similarity between temporally aligned observation pairs compared to kind of any other pairs selected within a single view sequence. However, TCN penalizes misaligned pairs equally. So, for example, these two misaligned pairs are penalized equally, when in practice, this pair is temporally closer observations should be more acceptable than this pair. And this is the change that we have made to TCN to obtain a more temporally smooth representation. So this multi-view setup now becomes a multi-domain setup in our case, and the negative pairs are now weighted by a temporally smooth distribution, so that temporally nearby observations are penalized less than temporally further observations. Finally, we wanted to make our representations also more RL friendly, more suitable for reinforcement learning training, since that is what we used for our trajectory tracking. So in order to do that, we added an additional auxiliary loss for training goal conditional policies in a cross-domain manner. What that means is that given a pair of aligned trajectories, we first select a frame from one domain as our current observation and a future frame from the other domain, and we train our representations in a supervised manner to regress the action that takes the current frame to the next frame. So by doing that, we are able to encode actions while learning the representation, and this is an effective representation as the observation and goal embeddings share the same space. To recap, to give you a full picture of the framework for obtaining our manipulator independent representations, We learn a high-level feature space that can match demonstrator and imitating agent observations. And this space has three main characteristics: cross-domain alignment, temporal smoothness, and reinforcement learning suitability. We are able to obtain this by using different forms of randomization, creating paired trajectories, training our MIR encoder with these trajectories, and a linear combination of temporally smoothness loss, TSCN, and a cross-domain goal condition policy loss for making the representations amenable to RL training. Okay, so time for some results now. I'm gonna immediately show how we're able to track a demonstration by a human hand. So here on the top right, I'm showing the sampled goals from a trajectory that was demonstrated by somebody in the lab, and we have two cameras for our observation. So it's a front left and a front right camera. And similarly for our imitating agent observations, we show how we are able to reach goals, and then new goals are fetched, and then our agent proceeds to reach those goals as well. And here it's the same agent solving the same trajectory, but with from a moving camera point of view. Before I show more qualitative results, I want to briefly talk about how we evaluated our method quantitatively. And because the tracking reward is something that is not very trivial to interpret, we chose a single type of behavior to imitate. In particular, we chose stacking for a number of reasons. First of all, stacking provides comparable complexity in the different environments that we have. It's a quite challenging task that involves multi-object interaction and rich contact dynamics, especially with the geometric objects that we have chosen. And most importantly, it allows us to have a shape reward that can tracking progress along the ways that is specific to stacking. So our stacking reward in simulation can serve as an evaluation metric that tells us when an imitation has reached an object, has lifted an object, and has stacked an object on top of another one. And that way, we can quantitatively understand, summarize rather, an imitation attempt without having to look at the video of imitation. And that's pretty important for the kind of evaluations that we have done. For our evaluations, we used 5 demonstration domains. And so we used the invisible arm that I've talked about earlier, the 3-finger Jaco hand. We used the real equivalent of our imitating agent. And then we used 2 settings where somebody in the lab used either the hand or a pickup stick to manipulate the objects. And we used 10 demonstrations per domain, and our evaluations included 100 trials per episode, as there is some stochasticity in our environment. So that totaled to 5,000 evaluations for each of the methods that we compared in the paper, and on which I will talk about in the next slide. For our comparisons with other methods, we used baselines from prior work that does feature tracking with small domain gap, and the baselines that we used were temporal distance classification, or TDC, simple goal condition policies, time contrastive networks, TCN, and cross-model distance classification, or CMC. And finally, we have our method, MIR, which stands for manipulator independent representations. Here I'm showing lifting success and stacking success. Lifting success, since all the demonstrations are successful stacking trajectory, lifting success amounts to roughly being able to imitate half a trajectory, and stacking success amounts to being able to imitate the entire trajectory. So what we see here is that all methods seem to be able to achieve some reasonable performance in imitating the lifting portion of the trajectories. However, our method was able to do quite a lot better. And when it comes to actually imitating the entire trajectory, so reaching the full kind of stacking um, performance, then we see that most of the other representations were not able to be used by the RL agent to imitate those trajectories. However, that is with the exception of the CMC baseline and our method, which did performed almost twice or more than twice as well as the CMC baseline. We also evaluated how important these different components to our loss were, and we start from from the TCN baseline and progressively add these components. So if you recall, for temporal smoothness, we tweaked TCN to make TCNs more temporally smooth, and that gave us a boost in performance both for lifting and stacking. And then finally, by making these representations, encouraging these representations to be more actionable, we were able to get our final performance. And time for some more videos. So here I am showing demonstrations by a Jaco hand at the top, and our imitating agent is tracking that demonstration on the bottom here. Here I'm showing the equivalent real world setup. So there's a demonstration in the real world, and again, our imitating agent is tracking it at the bottom here. And finally, I'm showing also how we're able to track a demonstration by somebody in the lab using a pickup stick to manipulate these objects. We also looked into trajectories that were not or behaviors that were not included in the training trajectories, and the trajectories used for training the representations. And in this case, we have stacking followed by unstacking. And this is a demonstration by a Jaco hand, and we're able to imitate that with our imitating agent and our robotic gripper. And similarly, we're also able to do that when the hand is not rendered. And for some failure cases, there were cases like this where, although we did track the trajectory, the gripper was not released. So that doesn't count as a success, that counts as a failure. And there were other cases where our demonstrations had some heavy occlusion on one of the cameras, and our agent was not able to deal with that. So as a conclusion, what I've talked about today is our work on making third-person imitation with reinforcement learning work for cross-embodiment scenarios from pixel space and with large domain gaps. And we discussed what was important for creating representations, manipulatory dependent representations that help for a cross-embodiment third-person imitation. And those were cross-domain alignment, temporal smoothness, and reinforcement learning suitability. And if you enjoyed this and you would like to learn more, please visit our website where we have also a link to our paper, or reach out to Yushan, Yusuf, or myself for any questions you may have. Thank you very much.